So now that we've talked about why glazes give ceramics color, we're going to jump back into kind of the basis for ceramics, and we're going to start by talking about clay. And so if the burning question in your heart is, what is clay? Basically, clay is just fine grained, crushed, and pulverized rock. So you have rocks, they undergo some sort of weathering, water, wind, ice, glacial movement, whatever, and you end up with clays. Now, clays, a few things about these that define them: they become plastic when wet, and that means they're moldable. The clay particles adhere and dry without cracking. So they stick together and they dry and they don't crack. And then when they're heated to a high temperature, that dry clay is converted to a rock-like mass. So next I want to talk about a few words that you will see when we talk about clay. So these are clay terms. And the first thing you're going to hear are clay minerals. And most of the minerals in clays are hydrated aluminum silicates. So when we say something is hydrated, that just means that it has some water that's associated with it. Then we also have clay deposits. This is a mix of clay minerals and other compounds. Okay, and so clay minerals, just hydrated aluminum silicates. If we talk about clay deposits, it's those hydrated aluminum silicates with other compounds that are all mixed in. When we talk about clay bodies, this is the clay that's used to make ceramic objects. And then we also have clay slips, which is a mixture of clay and water. So those are the different clay vocabulary words that you'll see throughout the rest of this module. I want us to talk about the clay minerals first. The clay minerals, so an example of an aluminosilicate mineral is feldspar, right? And so when we talk about feldspar is part of granite. So you can see granite here, right? Granite is a rock. It can break down. It can form clays. It has feldspar, mica, and quartz in it. And you can look further at those pure quartz and feldspars and micas. So this is what they would be as a pure form. But when you're looking at granite, that's an aluminosilicate mineral. And that's what it breaks. That's when it breaks down, it forms clays. So let's look at that process of the granite breaking down or weathering. So when we have that feldspar granite, it undergoes weathering. So that means we've got some water and it reacts with a CO2 in the air. And then it forms so this is kaolinite clay. It's an aluminosilicate. And there's also other minerals that it forms. It also forms SiO2. So there's some silica and potassium carbonate. So when it goes through weathering, all right, so when granite, feldspar goes through weathering, it forms the aluminosilicate. So there's the aluminum, there's the silicate, mineral. Now, let's talk about different types of clay. So if clay forms at the site of the parent rock, it's called a primary clay, which a lot of times we can say is 1 degree, like that primary clay, or residual clay, right? If clay is transported away from the parent rock by like water or wind or glacier movement, that's called a secondary clay. And we can represent secondary with 2 and a degree sign. 2 examples of primary and secondary clay is kaolinite clay. This is an example of a primary clay. It's usually found in pockets in the parent rock. And is very pure. Then we also have ball clay. Ball clay is an example of a secondary clay, and that contains more impurities. And some of those impurities are things like carbon or iron, and so that results in it being darker in color. Now, let's talk about clay structure and that plastic property that we talked about before. So the plastic property of clays is really a direct result of the microscopic and molecular structure of the clay. So if you look at this kind of rendering here, we've got a silicate layer, then we have an ionic layer, and then we have the aluminosilicate here. Now, so what's happening here is that the silicates and aluminates align in layered sheets, and it traps those water molecules in between them. So the silicates and aluminates align in layered sheets that trap the water molecules between them. Now that trapped water allows the sheets to slide over each other, making that clay plastic. So that's why it's moldable. So if you've ever molded clay, that's what's going on there. So that means it's able to bend without breaking. So the trapped water allows the sheets to slide over each other and that's what makes that clay plastic. Which when we say that, we mean it's bendable, it's moldable. So it's able to bend without breaking. So let's talk then about those clay deposits. When we talk clay deposits, you can have primary or residual clays. And like we mentioned before, these are generally found at the site of formation, so at the rocks. And they are coarse, larger particles with a low plasticity. Right? And they're usually quite pure. Right? And so kaolin was one of those examples that we looked at. And then we can have that secondary clay, which is also known as sedimentary clays. And these are the ones that are transported by wind, ice, and water from the original site. They generally tend to have very small particle size, which makes sense, right? As they're traveling along, they're going to break apart. And so you end up with a smaller particle size, right? And are usually not quite as pure, okay? Now, when we start to talk about clay bodies contain a really careful balance of clays. And so that's that primary and secondary clay, and that imparts plasticity and workability. So remember, clay bodies, that's what we're using to make these ceramics. And so you mix in your clays, either the primary or the secondary clay or some sort of mixture of both. Then you're going to add fillers. And these fillers aid in shape retention. During the firing. So you don't want to, make a really beautiful ceramic pot and it looks great and then it fires and it doesn't keep its shape. And so when we put it in the kiln, we call it firing. We want things to keep their shape when they go in. Then we also have fluxes. Now we had fluxes in the glass module as well. And so what the fluxes do here is they control the fusion or hardening point during firing. And what they do is they increase the strength of the fired product. So there are many different kinds of clays that you can purchase. There are these clay bodies. There's red brick clay. So I grew up in East Tennessee and people talked about red clay. There's natural stoneware. Clay. There's pure kaolin. There's ball clay. There's fire clay is another one. There's terracotta clay, which is like for earthenware. And so what happens with these natural clays is when you're an artist, you get all of these clays and you mix it all together to come up with your perfect recipe for your clay bodies. These are close-up images of the three different clays. This is a particular type of image called a scanning electron microscope. And that shows just the particle size of the clay. And so this particular clay has a really high plasticity. These two clays have a low plasticity, and you can see these are really defined particles, whereas these particles are not quite as well defined. All right, so they're sticking together a little bit better. But again, what artists do is they come up with their own recipe and they combine these. But these are different clays that you can combine and mix then with your fillers and your fluxes. So the fillers are just going to be these really high melting point materials. So this is the second recipe in making clay bodies. They're going to make the clay more porous. And control the water absorption of the clay. So there are a lot of examples of these that you can purchase. Grog is an example that you can purchase, which is the crushed fire brick of fired pottery. You can have aluminosilicates. You can add sand, right, which is really a mixture of silica and quartz. You can just add alumina, Al2O3, or just ground rocks or shells. So the fillers can be a lot of different things to give these different appearances of different types of ceramics. And then the last one that you would mix together would be a flux. Now remember, fluxes are going to decrease the firing temperature of those clay bodies. So we won't have to fire it quite as high, and that saves on energy and time. They form viscous liquids at high temperatures. They're going to melt and fuse with other materials to give glass-like texture. And so through that's going to cement those clay crystals together, and then it increases the strength of that fired finished product. Now, common fluxes that people run into are things like alkaline, earth, metal oxides. These are things like calcium oxide and magnesium oxide. And then your really common feldspar materials, right? So things like the potash feldspar or the soda feldspar or that nepheline cyanide that we talked about, any of those. And then calcite, which is sometimes called whitening, which is a calcium carbonate material, are also common fluxes. So again, every potter sort of has their own recipe for their clay bodies that they like, but they're going to contain one or more clays. They're going to contain minerals, and then they're going to contain the common fluxes as well as the fillers. Now, let's look at a typical porcelain clay body. So let's say we are going to make a porcelain clay pot, right? We would use 4 ingredients. So first we would start with kaolin, which is the clay. This would be our clay that we would mix in, right? It's a white clay. It's got really low shrinkage. The melting point of this clay is right around 1500 degrees Celsius. And then we'd mix in feldspar, and feldspar here would act like the flux. Okay, and what that's gonna do is that's gonna lower the melting point to 1300 degrees Celsius, and that's good for us as the artist. We don't have to use as much energy to heat it up. We can get to 1300 faster than 1500, so we can make more pots to sell. So that's really helpful. It also lowers the shrinkage of the material. So we don't want to make a pot thinking it's going to be one size and then get a teeny tiny pot out because that pot has shrunk. So the flux is really very important. Then we would mix in some flint. This would be the filler. This would be, this would increase the hardness. And then it would help with the glaze fit. And then we would maybe mix in another clay. Maybe we mix in some ball clay. So this is another clay. And you don't just have to have one flux or one filler. A lot of times, right, people have multiples because they're trying to get their perfect recipe that makes the best clay for their application. And so ball clay a lot of times will increase the plasticity of the clay. Right? So these would be 4 ingredients that you can mix together to make a clay body. Now, once you have your clay body and you shape your clay, and then the next thing you want to do is you want to fire your clay, and you put it in a kiln. And so we're going to talk about the firing characteristics of clay. So the first characteristic is it needs to be fusible. So it needs to deform and melt when heated on the microscopic level. It needs to be vitrifiable. it partially melts, right? But does not deform. And when that happens, it produces a dense, non-porous ceramic body. And then another firing characteristic is having refraction or being refractory. And that's just going to help it resist high temperatures, so it does not melt or deform. So maybe you're sitting there and you're going, hey, Dr. Pierce, fusible and refractory, those look kind of like the opposite. And you're absolutely right. So you may want a clay that's really fusible for one thing, right? And is really great, but you may want something that's refractory for something else. So these are just characteristics that we use to describe what's going on when we fire clays. Okay, and so sometimes they're good for one purpose, but maybe not good for another purpose. And so we're very purpose driven in what we use to make these ceramics. So let's talk about, now that we've defined some things about firing clays, let's talk about the process of firing clays. Now, this was first done over just open flame, but now we use ovens or kilns are used for firing. They're going to dry and heat the clay above about 900 degrees so that it partially vitrifies and hardens. So this oven or kiln is going to dry and heat the clay body above 900 degrees Celsius so that it partially vitrifies and hardens. So let's talk about the steps in firing. It's pretty straightforward. There are 3 steps. You increase the temperature over time. So you do this generally somewhat slowly, right? Then you hold at a peak temperature for some time, and then you cool it down very slowly, right, back to room temperature. So we heat it, we hold it, we cool it down. That's how you fire your clay. So let's look at different types of pottery. The color, the strength, the porosity, the hardness of the pottery depends on a couple different things. The first thing it depends on is the chemical composition of the raw materials used. The next thing is the surface treatment of the pottery before firing. Are we using a glaze, right? So glaze would be a surface treatment. We talked a lot about glazes giving color to pottery. That would be an example of a surface treatment. The temperature of the firing process helps us figure out what type of pottery that we're going to make. And then the redox properties of an atmosphere within the kiln during the firing. Now I want to talk about redox here. What redox is it's a process, a chemical reaction that happens when you have reduction and oxidation. And what happens here is in reduction, a chemical substance gains an electron. And in oxidation, a chemical substance loses an electron. Now, this doesn't really gain or lose. What's happening here is what's going through oxidation is giving the electron to whatever is going through reduction. Okay, and so that transfer of an electron is called a redox, and that's going to change the charge on your materials, which can change the color. So if we think back to, we said, hey, look, if you've got Fe2 plus or Fe3 plus, those color of those ions can be different. Well, what changes those oxidation states or those charges is this transfer of electrons. And that can change the type of pottery that you make if you have different redox properties within the atmosphere that helps that electron be transferred. So this results in all sorts of different types of ceramics that we run into. So we're going to talk about some of these. This is not an exclusive or inclusive list, but just really a sampling of all of the different ceramics we can see. So the first one we're going to talk about is terracotta. This is fired at a really low temperature. Right? It's about 900 degrees Celsius, and there's generally no glaze. Right? And so because there's no glaze, it is very porous. Right? And so an example of that would be these terracotta pots. We use these a lot of times for planting flowers. They're pretty cheap at a hardware store. So that's kind of the first example of pottery. Then the next example is earthenware. This is fired between 900 to about 1150 degrees Celsius. This pottery is stronger than terracotta and less porous. And then it generally has a glaze. And so because it has a glaze, that's where you get a lot of the really nice, pretty designs onto the pot itself. Now you can also have stoneware. I have an example of stoneware here for you. It is very strong and non-porous. It's fired at 1200 degrees Celsius to 1300 degrees Celsius. And what happens is that higher kiln temperature seals the pores. Right? And it came about in the early 1700s by a German chemist. He developed it. And these a lot of times are dinner dishes. So when we think about the difference between a terracotta pot and our dinner dishes, we would not want to serve food on a terracotta pot. It's going to absorb the oils and the liquid and the water from the food into the pot. Well, your dishes, because they are stoneware and those pores are sealed with the higher temperature firing process, you don't absorb any of the food into your plates. And so they're very reusable. Other ceramics that we hear about are bone china. This is really a lot of times called fine china. My grandmother called it your fine china. So this is an example of bone china. It's about 1250 degrees Celsius is where that is fired to. It's still that stoneware temperature. It's within that region, but it is defined as kind of that bone china or fine china. And then porcelain goes even higher. It's 1450 degrees Celsius. And so the porcelain that we think about, we can have porcelain dishes, but it's also made, our toilets and our sinks are made from porcelain. So that's another ceramics application as well. So now that we've talked about these different types of ceramics and the temperatures they're fired at, I want to talk about the kiln for a second. So this is a picture of a kiln, and we already talked about that the redox conditions of the atmosphere will affect your pottery. And so I want to give some words to that, where the redox conditions in the kiln play a role in the coloring of the ceramic, right? Because the charge on the metal in the glaze can change. So it can undergo, whatever metal it is, can undergo a redox reaction in the kiln while it's being fired, and it can change color. And that's why sometimes people who make pottery will say, okay, we're going to put this glaze on, and the glaze looks green, and they put it in the kiln, and when it comes out of the kiln, it's blue, right? So that's one of the reasons why it can change color. So, right, under oxidative conditions, which is oxygen in air, is how that's defined, at about 1100 degrees Celsius. If iron is present, you'll see a change from red to pink. And so that's an example of a change that you would see, right? If there's very little oxygen, present in the kiln, that's called a reducing environment, right? And ceramics generally take a darker color. Right? Now, so that reducing atmosphere, a lot of times when you have a kiln with a reducing atmosphere, it is a little bit of a challenge because we need oxygen for the fire to burn. And so this has a special name, a lot of times referred to as raku firing. So if you're interested in that and looking into that more, that's what you can explore. So let's look at the different stages the pottery goes through, or the clay bodies go through as they're fired. So the first stage is drying, and this is as it heats up from room temperature to about 25 degrees Celsius. And what's going on in this drying stage is the residual water is removed. Right? And this is done at a slow rate to prevent explosive vaporization. So nobody wants your pottery to explode. Okay. So I mentioned that, hey, that first heating up, we're going to go kind of slowly. We want to go slowly because we don't want all the water to evaporate all at once and it have explosive vaporization. Now the next stage is called dehydroxylation and oxidation, and this occurs from 250 degrees Celsius to 500 degrees Celsius. And what happens here is the lattice, or chemically bound water, is removed. So D a lot of times means something is being removed. Hydro a lot of times refers to water. So it's that lattice or chemically bound water in the clay body that's removed. The other thing that happens at this stage is if there's any organic matter that's in your clay body, it burns off. The next is vitrification. And this is what's going to depend, this is kind of the last stage of heating. So it depends on what type of ceramic you're trying to make. And that can range anywhere from about 850 degrees to 1450 degrees Celsius. And remember, when we talked before, I said, hey, look, all of these different types of ceramics go to different heating temperatures here. And that's that point of vitrification. And what's happening at this point is that your fluxes are melting. And when the fluxes melt, that means you have a glassy phase that develops, and that pottery is hardening. And so what goes on here is the clay then undergoes various crystalline phase changes. And those various crystalline phase changes give us the different types of pottery that we're looking for. Then the last stage is cooling it back down. So from wherever you went at vitrification, you're going back to room temperature. And what happens here, and you have to do this slowly, because if you do it too fast, you can get crystalline inversions. Right? And that ceramic can crack. So we have come to the end of our ceramic discussion, and just want to summarize ceramics and glasses, because we've talked about ceramics and we've talked about glasses, and there's a lot of overlap here because glazes that are on ceramics are that glassy layer. So I want to point out some ways that the ceramics and the glass are different. So one of the big ways they're different is ceramics are shaped at room temperature. Glass is shaped at elevated temperature. So we have to heat glass up to shape it. We don't have to do that with ceramics. Ceramics are going to harden when they're heated. Glass, when it's heated, it becomes more liquid and it flows and it hardens as it cools. Ceramics are very porous, and so we end up putting a glaze on the ceramics if we don't want them to be porous, that is a glassy glaze, and the glass is non-porous. And then ceramics have a microcrystalline structure with the aluminosilicates, whereas glass is non-crystalline. We talked about that a lot in that section, that glass, instead of being this non-crystalline, is amorphous. So this concludes our ceramic and glass lectures. As always, if you have any questions, please feel free to stop by my office.